For thousands of years, humans looked at a thunderstorm and saw the violent, uncontrollable wrath of the gods. Today, you control that exact same force with a button. But getting to where a city only goes black when we choose took centuries. The first recorded attempt to understand this force happened in ancient Greece, around 2,600 years ago. The philosopher Thales of Miletus was experimenting with a piece of amber, a hardened fossilized tree resin. When he rubbed the amber with wool, he observed that it pulled lightweight objects like straw toward it. He had documented static electricity. It took nearly millennia to connect that invisible pull to the sky above. In 1752, Benjamin Franklin flew a silk kite with a metal key attached during a thunderstorm. When sparks physically jumped from the wet key, he proved that the massive lightning bolts in the clouds and the tiny static sparks generated by rubbing amber were the exact same natural force. Understanding that lightning was a natural phenomenon was a major scientific breakthrough, but it left a glaring engineering problem. Static sparks happen in an instant and vanish completely. Because the energy dissipates immediately, you cannot use it to do actual mechanical work. In 1780, Italian scientist Luigi Galvani was dissecting a frog when he noticed its dead leg twitched violently after being touched by a metal wire. This observation led to a widely accepted, though incorrect, assumption that electricity was uniquely generated by living biological tissue. Alessandro Volta suspected the frog was merely acting as a conductor. He set out to prove that electricity could be generated purely by combining different metals and chemical solutions, completely removing biology from the equation. By 1800, Volta built the voltaic pile, recognized as the world's first true battery. He assembled it by stacking alternating disks of zinc and copper, separating each layer with cloth soaked in salt water. Here is a cross-section showing how a basic chemical battery works. The salt water chemically reacts with the zinc and copper plates. This specific reaction forces electrons to detach from the zinc and travel continuously through a connected wire. Instead of a single fleeting spark, you get a steady, unbroken flow. Achieving a continuous flow, an electric current, was humanity's first major victory over the electron. But batteries rely entirely on chemical reactions, and eventually those chemicals deplete. To build a modern grid, engineers still needed a permanent, endless source of power. The path to endless generation opened by accident in 1820. A Danish scientist named Hans Christian Ørsted noticed that whenever he ran an electric current through a wire, a nearby compass needle deflected. He had stumbled onto the reality that electricity physically creates a magnetic field. This observation caught the attention of Michael Faraday. He asked a brilliant reverse engineering question. If electricity can move a magnet, can a moving magnet create electricity? To test this, Faraday took a permanent bar magnet and physically slid it back and forth inside a hollow coil of copper wire. This schematic visualizes his breakthrough. As the magnet moves, its invisible magnetic field lines intercept the wire. This shifting field forcefully pushes the electrons within the copper coil, creating an electrical current without a single drop of chemical battery acid. This principle is called electromagnetic induction. To scale this up, engineers simply had to automate the movement by replacing human hands with water or steam. By attaching magnets to a turbine wheel and spinning it continuously, you create a massive, unbroken flow of electrons. Electromagnetic induction moved electricity beyond limited chemical reactions. It turned power generation into a mechanical process, proving that if you can spin a wheel, you have infinite power. By 1882, Thomas Edison commercialized this mechanical generation. He opened the Pearl Street Power Plant in New York, proving that electricity could illuminate entire city blocks by heating the delicate filaments inside his incandescent bulbs. But Edison's system relied on direct current, or DC, which suffered massive energy losses as it traveled over long distances. To keep the lights on, a coal-burning power plant had to be built in almost every single neighborhood. A young visionary named Nikola Tesla challenged Edison. Tesla championed alternating current, or AC, as the architecture required for a global grid. This split-screen comparison shows exactly why AC solves the distance problem. AC voltage can be stepped up using transformers, allowing it to travel vast distances with minimal energy loss. Once it reaches a town, another transformer steps the voltage back down to a safe level for a home. In 1895, the colossal Niagara Falls hydroelectric plant successfully generated AC electricity and transmitted it 25 miles away to Buffalo. It proved that Tesla's system was the only viable way to wire the entire planet, effectively ending the war of currents. Today, the modern grid is a continent-spanning expansion of Faraday and Tesla's machines. It still starts at a power plant, where pressurized steam, wind, or falling water spins a massive turbine to generate an AC current. Once generated, that current hits a step-up transformer and merges onto the high-voltage transmission lines. These lines carry the power across mountains and plains, making up the backbone of the national grid. As the electricity approaches a city, it exits those towering lines and enters a local substation. Here, the voltage is reduced to a safe level and routed into the smaller distribution lines that run through your neighborhood. Before reaching your appliances, the current passes through a final series of safety checkpoints. It moves through your home's energy meter and the miniature circuit breaker, which prevents electrical overloads, until it rests right behind your wall switch. When you flip a light switch today, you are instantly completing a physical circuit that reaches all the way back to a spinning turbine hundreds of miles away. It is a real-time triumph of engineering. Right now, this grid is undergoing its most radical transformation since Edison. For the first time in history, we are moving away from relying entirely on spinning mechanical wheels. We are now harnessing the photovoltaic effect. From rubbing amber stones in ancient Greece to wiring entire continents, capturing the electron represents the cumulative weight of human curiosity and our refusal to be limited by the darkness.